We're going to have a look at some simple circuit equations today, and we're going to build those up and get a little bit more complex. And we're also going to talk, as we do this, about some of the different circuit laws that apply. Now, this isn't exactly riveting, exciting material that you're going to every single day go, oh, wow, it's a good thing I understand Ohm's law and Watt's law so I can fix this car. However, if you understand these basics, it will save you from making quite a few mistakes down the road. So let's get started. So here we have a simple series circuit. In a series circuit, as you can see, there is only one path for current to flow or electrons to flow. Amperage is going to be the same no matter where in the circuit you would take your reading. So amperage is going to be the same throughout the entire circuit, before or after any of the resistors. The total resistance value in the circuit is going to be the sum of all of your resistors added up. So we would add 30 ohms, 55 ohms, 75 ohms in this particular case. Your source voltage, which is our battery, in this case we have 12.6 volts, is going to be equal to the sum of all voltage drops. And that voltage is going to get divided up between our loads. So what does that mean? That means that our 12.6 volts here has to be consumed by our loads or our resistors, and we will have no voltage returning back to source. So let's get started. We have the resistance values and we have our total circuit voltage. So if you remember from a few seconds ago, I told you that the total resistance in a series circuit is the sum of all resistors. We're just going to add up our resistors. And if we go 75 plus 55 plus 30, should give us 160. 160 ohms. Now, we can calculate our amperage and our wattage. So what I want to do is use Ohm's law and Watt's law next. I'm going to write down the formulas. So it's nice to just have them laid out visually in front of you to help you be able to, just make sure you get everything correct. You could also write it down as V over AR. It just depends what you're more comfortable with. This is the way that I was taught and shown, and so this kind of sticks in my head. Although realistically, using your voltage, amperage, resistance, that might be a little bit more of a straightforward, less likely to make mistakes. Regardless, so let's solve for our amperage. What is our amperage? Amperage is our voltage divided by the resistance, which is 12.6 volts divided by 160 ohms, and that gives us 12.6 divided by 160, 0.079 amps. Now, when you're going to do your calculations, pay attention to how much precision you're after, because if I were to use 0.07875 instead of 0.079, I would get slightly different answers, with the more decimal places we use being the more precise. So let's solve for our power. Our power is our amperage times our voltage. So I already have my amperage in the calculator. Multiply that by the voltage, and I get 0.992 watts. Cool. What else can we solve with the information we have? Well, based on the series circuit laws, we know the amperage is going to be the same anywhere in the circuit. So we have our amperage readings. That's pretty cool. Now we just need to solve for our voltage and our power. And what's interesting here, so this voltage, that is going to be the voltage consumed by each resistor. So R1 is going to be the voltage that's consumed or dropped across resistor 1, and then the same goes R2 and R3. Let's do some calculations. So E, our voltage, or you could also write it down as, voltage drop, equals, and this is R1, so amperage times resistance, 0.079 amps times 30 ohms, 2.37 volts. And then we just have to do that 2 more times. 55 ohms, 4.345 volts, 75 ohms, 5.925 volts. Now, if we add all 3 of these together, they should equal right close to 12.6, our total voltage. We might be slightly off because of our rounding, so it should at least be in the ballpark. Let's do that just to make sure. 2.37 plus 4.345 plus 5.925 gives us 12.64. So we know that we're pretty close. We've just double checked our numbers there to make sure we've got them right. And now we can calculate our power. And when we're calculating our power, what's important here, our total power, our total wattage was calculated using our total circuit voltage. The individual resistor or load power needs to be calculated based on the voltage consumed at each resistor so that we can get an accurate answer. So this would be for R1, 2.37 volts times 0.079 amps, 4.345 volts, 5.925 volts, 0.468 watts. Well, I didn't do number 1 there. Let's go back. 2.37 times 0.079, 0.187. So if we add all of those up, they should be close. Again, remembering we're going to have some rounding errors in there. 0.995, and we had from our total calculation 0.992. So I'm very happy with that. We've just double checked to make sure that we did all our calculations correctly. So that is how to solve for your unknowns in a series circuit. Next, let's have a look at a parallel circuit. So the laws are a little bit different in a parallel circuit. Now, our applied voltage to each branch, so our applied voltage, our voltage total in this particular circuit is 14.7 volts. We are going to have our source voltage is 14.7. That will apply 14.7 to R3, R2, and R1. So what that means, we could just fill in our table right here. 14.7, 14.7, 14.7. Cool. Now, the current is going to be different in each one of these branches depending on the load, depending on the resistance. Each branch is going to consume or drop the full source voltage, which is 14.7, and there will be 0 volts returning back to source. The total circuit resistance is going to be equal to or less than the lowest resistor in the circuit. The resistance formula for this one is a little bit more complex than just adding them together. Our total circuit resistance would equal 1 divided by, open bracket, 1 over R1 plus 1 over R2 plus 1 over R3. If we had more than 3 resistors, we'd just continue adding on, close the bracket. And the sum of the branch current flow is going to be all of the current flow total. So we'd add up the individual amperages to get our total circuit amperage. Let's get started on this. Okay, so what can I calculate? Well, I can figure out what my total resistance is by using my formula here. So RT equals 1 over, open bracket, 1 divided by 7 ohms plus 1 divided by 15 ohms plus 1 divided by 37, close bracket. RT equals. Now, if you have a regular non-scientific calculator, you're just using your phone in basic mode, what you could do is go through and do these calculations individually and then do the entire circuit. Since we have a scientific calculator here, or if on your phone you just select the scientific calculator mode, you can do this all together and get a slightly more precise answer because you won't have the rounding errors. So we go 1 divided by, open bracket, 1 divided by 7 plus 1 divided by 15 plus 1 divided by 37, close bracket, equals 4.227 ohms. To double check this, now remember that circuit law in the parallel circuit, total circuit resistance has to be equal to or less than the lowest resistance value in the circuit. 4.227 is less than 7 ohms, so that abides by that law. That's pretty good. Okay, wicked. Now that I've calculated my total resistance, I'm able to calculate my total power and my total amperage. So let's do that. Let's do our amperage first. A or I, depending on which method you want to use or what letter designation, doesn't matter, it's the same thing. Almost the same thing. I suppose I stands for your current, where A is the actual unit, because you could also have milliamps, which would be a little bit different. But anyhow, so our current is equal to E divided by R, which is 14.7 volts divided by 4.227 ohms, which gives us 3.478 amps. And then we'll calculate our power, which is measured in watts. And that's our current times our voltage. So that would be 3.478 amps times 14.7 volts. And that gives us 51.127 watts. So from here, what else can we solve? Well, pretty much everything, because we have our voltage, we have our resistance, so we can just use Ohm's law to find our current, and we can use Watt's law to find our wattage, and then we can add them all up to double check and compare them to our total to make sure that we did our calculations correctly. So let's do that. R1 current equals I times E. So R1 current is E divided by R, your voltage divided by your resistance. So we got 14.7 volts divided by 7 ohms. That'll give us 2.1 amps. And I would expect this, being my lowest resistance, to have the highest amperage in this particular circuit. Because as resistance goes up, amperage goes down. As resistance goes down, amperage goes up. Solve for R2. 14.7 volts divided by 15 ohms. We have an amperage reading of 0.98. Does that make sense? We got a little over double the resistance and a little less than half of the amperage. I'd say that checks out. Let's do R3. 14.7 volts divided by 37 ohms, 0.397 amps. So add all those together. 3.477, and we have 3.478. So that is darn close. I'm happy with that. That means we did those calculations correctly. Let's finish this off calculating our power. So P equals I times E, which for R1, we have 2.1 amps times 14.7 volts, 30.87 watts. R2, R3. 14.406 watts, which is about half what the first one was. Makes sense. R3, 0.397 amps times 14.7 volts equals 5.836 watts. Awesome. And if we add all these up, they should be close to our total wattage. Let's do that. 51.112, 51.127. Very happy with that. So we just did all our calculations and double checked all of our work. Awesome. Let's scale up the complexity a little bit. So here we have a series parallel circuit, which is somewhat similar to most circuits in an automotive application, as they are protected by a fuse that is in series with the circuit, and then everything else, the loads in the circuit, are typically in parallel. So this is a little bit different because the load here is in series and we have some parallel loads. But let's use this as a nice basic circuit to learn how to do these calculations, and then we'll look at one more that'll get a little bit more complex. So let's break this down and simplify it, because we have series parts of the circuit, we have parallel parts, so we have some series laws and some parallel laws that kind of apply here. So we can't just add our resistances up, because, well, R2 is in series with R1 and R3 is in series with R1. R2 and R3 are in series with each other. So the first thing to do in this situation is let's break down the parallel portion of the circuit, because we can figure out what the total resistance is and kind of treat that the same way that we would treat a series circuit. So essentially what we're going to end up with would be just a single path, like so. So let's do that. We're going to have to use our resistance formula again. 1 divided by R1 plus 1 divided by R2. And while I'm here, E over IR, P over IE. Pi. Okay, so our RT of R2 and R3, 1 divided by 1 over 13 plus 1 over 36 equals 1 divided by, open bracket, 1 divided by 13 plus 1 divided by 36, close bracket, equals 9.55 ohms. So essentially, this is our circuit now. Or we could clean that up a little bit, and it would basically look like this, where we still have R1, and then we have R2 and R3 combined for the total resistance between those two. And now remember, in a parallel circuit, total resistance has to be equal to or less than the value of the lowest resistor, which 9.55 is lower than 13. So I'm good. I'm happy with that. Now, can we add these two up to get our total circuit resistance, our actual RT? Absolutely. So we will have 31.55 ohms. And this is where understanding your circuitry laws, what we talked about earlier, is very important, because without that understanding of the circuit laws, you're not going to be able to break something like this down. Okay, cool. So now that we've found our total circuit resistance, we can calculate our amperage and our power just like before. Our amperage total, I remember the amperage is our volts divided by resistance. It's 13.6. That's basically the same. We have a running vehicle in this situation. That'd be system voltage. Volts divided by 31.55 ohms. And that would give us 0.431 amps. Cool. Power, I times E, which in this particular case is 0.431 amps times 13.6 volts. And that would give us a grand total of 5.8616 watts. Cool. So we've been able to calculate the totals for our circuit. Can we break those down further? Yes, we can, because now we can calculate the individual voltage drops. So that will give us the voltage drop on R1. And then remember our circuit laws, the voltage applied to a parallel circuit will be the same on each branch. So this R2, R3 combo here, whatever voltage is applied to this is the same as the voltage applied in this circuit. So we're going to be able to find R1, and then R2 and R3 are going to be the same. Let's do that. Now, remember, again, current. So this is a series circuit. Our total current is going to be 0.431 of an amp. So anywhere in the circuit, you have 0.431, 0.431 amps. However, when we go back to our original circuit in parallel, that 0.431 is going to be split up between the two different loads. So we can't write that down for R2 and R3 because remember, in a parallel circuit, the current is different based on the load. 2 ohms, voltage equals 9.482 volts. Cool. So what's left over? We can do our calculation here, or we could take our total, subtract R1, and that would give us the answers for R2 and R3. Let's do the calculations for accuracy's sake. Remember, we're not using our individual resistance values. We're using the total resistance value here, which is 9.55 ohms. And that gives us 4.116 volts. I'm not sure if you've noticed this, but if we were to add 9.482, 4.116, 4.116, we're going to get a number that's much higher than 13.6. You did notice that, right? You can't add the R2 and the R3 because they're in parallel. So remember to pay attention to your circuit laws in the different portions of the circuit. Now that we have our voltage drop, we can use the individual resistances to calculate the current in our parallel portion of the circuit, and then those two should add up to 0.431 of an amp, because remember, current's going to be the same everywhere in a series circuit. So let's do those calculations. I'm just going to use a different color to try to help keep everything a little bit easier to follow. This paper's getting a bit busy. So we're looking for R2 amperage. Yes, very good. So our amperage is our voltage divided by the resistance, which is 4.116 volts divided by 13 ohms, and that gives us 0.317 amps. Now let's do the calculation for R3 amperage. So it's still E divided by R, which is 4.116 volts divided by 36 ohms this time, which gives us 0.114 amps. Now if we add those two together, we're going to get, wow, look at that. We got our exact amperage. So we've just verified that we did those calculations correctly. And now we can calculate our wattage just the same way as we did before. So whenever you have a series parallel circuit or a circuit that's getting more and more complex, break it down to its simplest form and find whichever unknown you can first, especially understanding the circuit laws to help you fill in some of that information, and then make the calculations as you go, keeping those circuit laws in mind. Let's take care of the power right now. The power on R1, I times E, rip, that worked out, would be 0.431 amps times, now again, remember we're not using our total voltage, we're using the individual voltages dropped across each resistor. That gives us 4.087 watts. Cool. R2 power, again, I times E. So I, this time, is 0.317 amps times 4.116 volts, which gives us 1.305 watts. And then for R3 power, I times E, 0.114 amps times 4.116 volts, 0.469 watts. And let's add those together to see if they equal our total wattage to verify we did all our calculations here correctly. 4.087 plus 1.305 plus 0.469 equals 5.861. Look at that. We were very close on that one. So I am very happy with that. Want to do it again? Let's step it up one more time and get slightly more complex in our circuitry. So it's a very similar series parallel circuit, but now we have a series portion of the circuit, a parallel portion of the circuit, and another series portion of the circuit within the parallel portion of the circuit. First thing that we should probably do is simplify this circuit as much as we possibly can. So we can add R2 and R3 together to create a combined, or find out what our total resistance is of this branch. So R2 plus R3, that is 137 plus 24 ohms. Carry the 161 ohms. Yes, cool, I get things right every now and again. So essentially, what we've done now with our circuit, our power source, we still have R1, which is still 77 ohms. R4 is still 36 ohms, but our R2, R3 combo is 161 ohms. Cool. That looks a little bit less intimidating than that. Could we do this again, just like we did in the last circuit calculations? And then we could turn our circuit into something like this. Yeah, absolutely we could do that. So we just need to use the right formula here. And remember our formula for resistance in a parallel circuit? And I always just like to write this down so I have it in front of me, even though I know it. E over IR, P over I E. Pi. Okay, let's do our calculations here. So this is going to get a little bit busy because there's quite a bit to do in this. So RT equals 1 divided by 1 over 161 plus 1 over 36. Don't forget your brackets. 29.421. Cool. That's a lot less intimidating, isn't it? Simplify your complex circuits into their most simplest form using your circuitry laws, and you'll be just fine. So let's fill this in. Let's do our calculations. Can we add R1 plus our R2, R3, R4 combo? Absolutely we can, and that would give us our total circuit resistance. 106.421 ohms. Cool. Now, just like before, we can calculate our total current and our total wattage, and then work backwards from that to get back to our full original circuit. Calculate our total current. I equals voltage divided by resistance, which is 15.1 volts divided by 106.421 ohms, which is 0.142 amps. That is a low amperage circuit. And again, P is I times E, which is your amperage times your voltage. 0.142 amps times 15.1 volts. And I like to, even in my calculations, I still like to write down my units just because it makes it easier to keep track of everything if I do make a mistake and I have to work back through to figure out where I made said mistake. 2.144 watts. With this information now, we can make some more calculations and figure out what our voltage is. So if our total voltage is 15.1, and that's going to be divided between the loads of our series circuit, we can calculate, well, let's see here. Our amperage, we know, is 0.142. Now, remember, this part, this resistor, that is our total resistance. The amperage is going to be different in each branch here. However, that total amperage, because this is a series part of the circuit, you'd measure that amperage number here, or here, or here, or over here. So amperage for R1, 0.142. Very good. Here's a hint. R2 and R3 are going to have the same amperage as well as each other as well. Not as R1, but as R2 and R3. Cool. So I have my amperage. I can calculate my voltage drop. I times R equals 0.142 times 77 ohms equals 10.934 volts. Well, okay, does that make sense that the higher resistance value is going to take up? Well, we have basically twice the resistance value there, a little bit more than what we do here, and it takes up a little over double of the voltage of what's going to be left for the rest of the circuit. Yeah, that does make sense. Okay, so now here, the same thing. I times R. Now, we know that we have 0.142 amps applied to this whole portion of the circuit. So we can use that number here, 0.142 amps times 29.421 ohms. That gives us 4.178 volts. Cool. So if we add those two together, is that going to be close to 15.1? Absolutely it is. Okay, very good. I have 4.178 volts applied to this parallel portion of the circuit, which means R4 is going to drop 4.178 volts. Cool, which means I can calculate my amperage at R4, which is also pretty cool. R4 amperage is going to be 4.178 volts divided by 36 ohms, and that gives us 0.116 of an amp. Well, you know what? I could go back one step here, and I could use the formula again, Ohm's law, to calculate my amperage on this branch, remembering that it's going to be the same over R2 and R3. So let's do that. R2, 3 amperage equals, well, how much voltage do I have? 4.178 volts, and that's going to be divided by, I didn't leave myself enough room there, divided by 161 ohms, and that will give us 0.026 of an amp. Wicked. And now remember, for R3 and R2, that's the same. Pretty cool. If we add, now remember, this is a series parallel circuit, so we can't add everything up. But in a parallel circuit, if we add the amperages, they'll equal our total circuit amperage. Now the amperage is going to be the same in R1 and R3, so if we were to add our amperage from this circuit drawing right here, that should give us our RT. So if we were to take 0.026 plus 0.116 and add them together, 0.142. 0.142. We just double checked. We did our current calculations correctly. That's pretty cool. We're getting there. It's a little bit tedious to get into these more complex circuits, but they're totally doable if you just break them down one step at a time. Let's see here. So our voltages, we know what R1 is. We know that R4. Now we need to calculate R2 and R3. Well, if we have 4.178 applied at this branch, we just go back through Ohm's law again, using our current and our resistance. You multiply those together, and that will give you your voltage drop. And if we add those two up, they should be the same as the applied voltage, which they are, or right close to it. Again, rounding errors. So cool, I am happy with that. And then we can use our Watt's law one more time to calculate our wattage, and then we'll finally be done with this. So let's start at R1, I times E. And for the rest of these, I'm just going to go ahead and do the formula in my head, but you can watch here on the calculator. So I times E. And if we add these all up, we should get our total wattage. Because remember now, every load in the circuit will consume wattage. And just for fun, for very, very rough numbers, 1 horsepower is equal to about 746 watts. More precisely, it's like 745 and change, but for our purposes, that's a general number. That's close enough. Add those all together and we get 2.147, which is very, very close to our calculated total. So I am very happy with that. We have taken a much more complex circuit than we started with, simplified it, and then worked backwards to fill out all of our unknowns. So I hope this helps give you an understanding of some of the circuitry laws, Ohm's law, Watt's law, how to calculate for your unknowns, and a little bit about circuit behavior. I hope this helps. Let me know in the comments what else I can do to help you out. Thanks for watching. Have a good one.